All yours. Thank you. Thank you so much. Thank you so much, Ali. I mean, there's not a lot of you, so if people wanted to move forward a little bit, make this somewhat less formal, welcome. Because otherwise, I felt like I'm constantly shouting at people. So my name is Dennis. I work for PTL, we're a Christchurch company. We do have branch here in Auckland, which is why I come up here every now and then. First of all, thank you so much, Ali, and also thank you so much to ASG for inviting me to come along and talk about mass timber fire safety. So a bit about my background. I'm a fire engineer. I don't pretend I know structural at all. So my apology if today's presentations sounded a little bit fire heavy. I try to talk as much about structural component as possible to make it sort of interesting for you guys. And I would say, given that this is the amount of people, I would say that, look, if you have any question, raise your hand. We can have a sidetrack bit of discussion. I don't mind that. So we'll kick off with the presentation. So this is the outline of my presentation. So we're going to start just talking or introducing about fire. What is it about combustion from the perspective of how we measure it in terms of energy release rate. Now, if you stick a fire inside a compartment, what happens? So really, this is just to give you a bit of a background about fire, a little bit about the jargon that I'll be using, so that you'll be able to follow parts of these presentation. And then next, we're going to talk about mass timber structural system. The word system is important, so we're not looking at specific component and try to understand their performance. Of course, we have to, but eventually, when we come to build buildings, we're always talking about system. We're always talking about components being put together, how they interact, how they perform with one another. And then point number 3 is a little bit of a rant from me. Basically, I will be telling you about my concern, the fire challenges when it comes to a mass timber structure. What do I worry about? Most of the time, these are things that you don't worry about. But because, again, we're talking about system, so it's quite important for us, fire and structural, to communicate, to pass on information, relevant performance, so you could do your structural fire design properly. So there's a few components in here. I'm going to talk a little bit about compartment fire dynamics. You wonder why? Because that's what drives a lot of our design calculation and also assumptions, eventually sort of arriving at a char depth, which is a parameter that you will be using when you're designing your structural system for fire. When it comes to mass timber, I'm concerned about delamination. You might wonder what the heck delamination is. Anybody done a mass timber project or structure before? Raise of hands. Ali, a couple of them. So appreciate your feedback at the end of the presentation, and tell me a little bit, what are you concerned about? I guess from a fire perspective. Strength reduction. So if you're done the design before, at elevated temperature, timber will lose its strength quite rapidly. And it's a bit dark, I get it, when we talk about fire challenges, but not all hopes are lost. We will then talk about some guidelines that we have. I mean, these are not the latest and greatest. A lot of stuff is still under development, but we're going to look at what happened when the fire engineer is on a prescriptive design. Because the information that he or she might pass on to you, structural engineer, might be quite different from when he or she is doing a performance-based design. And what are the solution that is out there to kind of try to tackle some of these concerns that we have in terms of delamination or strength reduction. And then we're going to finish up the presentation with a few case study projects. And the whole idea here is to reinforce the concept of coordination. And whatever you wanted to call it, PN22 design coordination, so be it. Or you just simply wanted to talk about, let's sit down and have a discussion about the science and the logic and the system of it, that's fine too. Like, whatever you wanted to call it. But the important message here is a building design must be coordinated. Some decision will have to be made. Maybe it's not the greatest, but it is what it is, right? All right, so let's move on a little bit. So what is fire, right? Now, you will see that the video will start playing. What we have here is a cone heater, which is our heat source. We have a bit of a piece of upholstery furniture, which you're sitting on at the moment, being imposed to the heat source. Now, what you can see on the background is the heat release rate curve. So this is actually how we quantify or define a fire. So heat release rate, the unit is kilowatt per meter square of fuel surface area. The horizontal axis over here is time. So what's happening here is, okay, your solid ignited, all right, it's going through its growth phase, and eventually you will see it reaches its peak heat release rate, it will plateau, and when the fuel is consumed, it will decay. So flame is a chemical reaction. So when we say solid is burning, all right, in reality it's actually the gaseous fuel that is coming off the solid that is burning. So wherever you see a flame, basically what you're witnessing is the fuel gases interacting with the oxygen and producing the flame. The flame is a chemical reaction, basically. So this phenomenon here is fairly complex. All right, we like to deal with single variables, and whenever you have three variables, heat source, fuel, and oxygen concentration, which could all change, then you have a fairly complex kind of problem. Now you might wonder, like, okay, why has the fire reached a plateau? Why does it not continue to continue to increase? Well, because it's being governed by the heat source, right? So if I crank up the radiation level of this cone heater, I will change the shape of my fire, right? Instead of being flat, it might create some kind of a peak if I crank it up too much. Why? Because the gaseous fuel is getting more and more excited by the heat source, so they react much faster, right? And now you can see that, well, okay, the fire goes through the growth, the peak, and the decay. So every fire goes through this phase, whether it's out in the open or if you stick it inside a compartment, it will go through these phases.
Why does it go up and down on the top?
It is a bit of a plateau, so if you look at the value, it actually doesn't change much. It sort of hovers about 350. My apology, the wording is a bit small, but it is really a plateau. So if you increase the heat source, you might get a taller peak. So it changes slightly. So how do we quantify fire? Again, a little bit of basis, right? So we quantify energy release in joules. More commonly, we will refer to kilojoules or megajoules. You will see these units come about throughout our discussion. It's a little bit like force, Structural engineer deal with kilonewton, megapascal, that sort of stuff. Now, the area underneath the curve that you see before, if you integrate all that area, that will give you the total energy release during that fire. And we have a term for the energy release. That is the fuel load. So you will hear me mention about fuel load in our sort of subsequent discussion as well. Now that's area underneath the curve, but the curve itself is the power of the fire. Okay, it is in watts. It's joules per second, or more commonly, kilowatts or megawatts. That's the sort of fire size we deal with. Why? Because this picture here gives you the depiction, right? If you have a match, you strike it, light it, that's about 5 watts. That's a no fire, don't worry about that, right? If you have a pool fire, which is about 20 mils diameter, okay, heptane pool fire, you'll get a peak of about 200 kilowatts, all right? That's a bit of a concern, right? Now, if you have a couch, which is, sitting inside your living room, for example, if that ignites at its peak, it will generate 1 megawatt, or 1,000 kilowatt. All right, a bit more concern as well. Now, if you have a tanker and you stick it inside a tunnel and it becomes fully developed, you might be looking at 100 megawatt. Now, that is a big concern. Right? So these are the different fire sizes that we have. Now, how do we measure these heat release rate? Now, the video that you've seen before is actually an experiment, oxygen depletion calorimetry. So basically, we sample the smoke that comes off the fire and figure out how much oxygen has been consumed by the fire, and then you can work backwards and calculate these fire sizes. So the measurement is actually pretty accurate. Now, why am I telling you all this? Because this technology of measuring fire size to heat release rate is only about 40 years old. Before that, we used to believe that temperature is the proper measurement of the power of fire. But until one point, we realized that as the fire gets bigger, the temperature doesn't go up. It just stays around a constant value. So now if you stick a fire inside a compartment, the fire will go through these phases. So you look at these curves, it's pretty similar to what we have before. All right, you have an incipient phase. Your fire will then enter a growth phase. During this period of time, what's happening is your fire will probably be restricted to just one item, right? The first item ignited, right? And over this incipient and growth phase, the people have time to escape, right? You need to get out. Because very soon, you get into the short phase that we call flashover. What is flashover? Flashover basically means that any fuel that will burn inside a compartment will ignite at that point in time, all right? So so you will see that the fire size, obviously go up quite rapidly. So beyond the flashover phase, you enter the fully developed phase, right? So this is where you see large flame shooting out of your compartment. The whole reason is there's not enough oxygen anymore inside the compartment for the fire. And you have a lot of unburned fuel, which is leaving your compartment, and they meet fresh air outside. So they burn all outside of your compartment. Now in this phase, okay, if your people have not left, they probably is already dead inside the room of origin. But then there's also people entering the building at that time, which is the firefighter. They have breathing apparatus, they have water, so they're trying to go in there and do their search and rescue. Now temperature, what's happening with temperature? And temperature is something that structural engineer will be interested in. You couldn't care less about the fire size, but temperature is important, right? So during growth phase, it doesn't really concern you because it's only about 200 degrees Celsius. Right? It's more for the people, really. At flashover, you get to about 500 degrees Celsius. And beyond that, for a really long duration of your fire, it's more or less a constant temperature of about 900 degrees Celsius. And you wonder why 900 degrees Celsius? That's the temperature of what we call a diffusion flame. Diffusion flame is where the fuel molecule will need to travel to meet an oxygen. And this is more or less the scenario that we have whenever we have accidental fire, right? We don't deal with what we call pre-mix, which is the flame you use for cooking, right? The gas and oxygen, the fuel and oxygen is all well mixed and you have blue flame. We don't deal with that kind of situation. Our situation is diffusion flame. They're bright, they're yellow, they radiate a lot, right? Now, so this is the stage where, all these structural consideration in regards to fire sort of come in. So it's actually a very long duration of a fire if you consider, a fire inside a building. Right, so that's introduction. So now I can assume that you're all fire engineer, you know what I'm talking about whenever I use a jargon. But we're going to go in and just have a quick look at mass timber structural system. All right. So what do we have? We have LVL, glue lamp, CLT, okay, different members of this mass timber family, all right. We have CNC machine, okay, computerized numerical control machine that allowed us to produce mass timber element in a very timely cost-effective way, reduce the amount of waste we have. Architects love to use timber because it takes their design objective in terms of architectural aesthetic. They like to use it where possible. And, there's a whole other series of research when it comes to sustainability. I'm not gonna go into it. Timber is green. Timber sequesters carbon. You would have heard of these many times. And from an end user perspective, there's a lot of psychological, physiological benefit for people. So you feel very calm already sitting in this room full of timber, isn't it? Now, the thing here is the lamella. So all these mass timber, they have layers and layers. I call them the lamella. They don't just come together. They need to be held together. So as part of the system, you need to think about, what kind of adhesive are used for this timber. And there's different adhesive. From a fire perspective, there's different adhesive. There are adhesive that perform well under heat, and then there's adhesive that doesn't perform so well under heat. All right, they will fail, and as a result, your layer will start to fall apart, start to delaminate. Now the thing is, now we come up with all these elements. Now we have LVL, CLT, and glue lamp. All right, walls and floor doesn't just come together. You need connections to put them together. Beams and columns have to be joined together, right? So there's different connection for you to think about. There's screws, there's plate with dowels, rivets, nail plates. I think, you know more about this than I do, all right? Or at least from my structural colleague in my office, they often talk about connections. How do we detail this? How do we protect it from fire? That sort of thing, right? And it becomes more complicated when you start putting things together. Like, for example, you will have CLT floor sitting on steel beam. The steel beam will have an end plate that is being fixed into a CLT wall. All right, you might have, as part of your seismic design, you have the lateral restraint system. So in this case, you have, here you have EBF. Basically, steel column going through your CLT floor. The floor sits on top of a beam. You have brace coming in at an angle, that sort of thing. All right. So what I wanted to say here is, it's very complex stuff. So we need to coordinate. So there needs to be a conversation, a dialogue between structural engineer, fire engineer, and also architect, all right, to achieve a building design objective. Now I'm going to talk a little bit more now about my perspective of mass timber fire safety, touching on compartment dynamics, touching on, the aspect of delamination, and also strength reduction. So why do I worry about compartment fire dynamic? Well, that's the source of all problems. But sometimes I don't care about fire dynamics. And you will ask me why, because I'm on a completely different pathway. So fire design, there's prescriptive design, and then there's performance-based design. Under prescriptive design, a lot of time I don't care about the fire dynamic at all. I know it's going to happen, but I just do not care. I'm doing design by prescriptive means. What does that mean? It means that I'm reading a table. The table will tell me what the fire resistance rating is, and also will tell me how much exposed timber surface I'm allowed. And I'll basically tell that to my design team. I'll tell you, the structural engineer, that I need 60-minute FRR. That's it. All right? And then if you happen to have to calculate a char depth because you're trying to size your beam, size your column, or you're trying to design a specific connection, then I will say, use the standard fire characteristic. All right? The charring rate. Anybody know what's the standard charring rate? Want to have a go? Yeah, exactly. So just go use that. Some people might challenge and say, look, I've seen an experiment. It's going at 1 mil per minute. Fire engineer doesn't care. Just use 0.65. I'm on a prescriptive design. Don't bother me about it. Right? No, we have to communicate. I will explain to you sort of why shortly. But prescriptive design. Read the table, use the standard value, and off you go. The reason for that is because a lot of prescriptive design is for fairly simple building where the risk is really just not that significant, okay? But not always. Not always. Like, there's a lot of situation where quite easily a fire engineer will find himself in the performance-based region where he will absolutely have to think about compartment fire dynamic. Why? Because it's a completely different pathway for us. Right? A prescriptive design, we read the table and then that's it. But a performance-based design, we get questions about fire dynamics. Have you considered the contribution of timber? Have you considered how much window is breaking? So it's a complete different ball game. So some of the slides that I'll go through will explain this a little bit further. But for now, when we consider fire dynamic, have a look at this picture. They might all look like flame to you, but if you look closer, they are different, okay? Most of the time, for my performance-based design, I'm assuming a full room involvement. These two examples is a full room involvement. So basically, the condition inside the room is uniform, 900 degrees Celsius throughout. That's my assumption. I do my calculation that way. I figure out what's the ventilation. This far, very well ventilated. You can see a lot of opening. That far might not be so well ventilated. They will have different char depth, okay? And I will need to pass that char depth information to you for you to complete your structural design, because you might have a column in there, you might have a beam in there, you might have a wall in there, right? Now this is more of a worry, right? So these two situations, you find it in a lot of places. You find it in an apartment, because apartment is not that big, right? Apartment is like 100 meters square, maybe 200 if you're rich, right? And that's it, okay? But open plan office, you're talking about what? 1,500, 2,000 meters square of just endless area, right? So the fire dynamic can be quite different. The fire might travel around inside these open plan configuration. And that is something that a lot of fire engineer or a lot of fire researchers are still scratching their head on about. So that's the limit of our knowledge, if I were to put it in plain words. Like traveling fire, localized fire in an open plan configuration, that's all research stuff at the moment. So what I wanted to kind of show you here, all right, is the impact of ventilation on the fire, right? What are all these, what are all these different curves? So we have basically the time temperature curve, all right? People heard about the time temperature curve when it comes to structural fire design, all right? So I wanted to point your attention to the red line. The red line say ISO 834. What is ISO 834? ISO 834 is the standard fire test. That's where a lot of our floor system, wall system, fire stop get assessed to, right? That particular test. So you can see if you just compare the time temperature, these are all time temperature curves. If you just compare the ISO curve to all these other theoretical, realistic fire, you will see that this curve is only one of the many potential fire curve that is out there. So really, this is only for testing. It is not really a real fire. It's just one of many, right? So if you move through the slides, we, all the way at the top left corner, what we have is a very small window situation, right? So the fire that we have here is lower in temperature, but longer in duration. So it's a fire that will burn for longer, but at a lower temperature. Over here at the bottom right, when you have a lot of window, right, what happens is you have short, sharp fire, right? Fire that has high temperature, but only burn for a really, really short duration, okay? And now you might wonder why. So I wanted to tell you the sort of idea about this. If you think about your oven, right? You have an oven that is going, right? But then you only open it a little bit, okay? So a lot of heat is still within your oven. Now, if your oven is made of timber, then the timber will char quite heavily in that particular scenario. Now, this scenario down here, what is it like? This is like when you're sitting at a Japanese restaurant, all right? And you're having a bit of teppanyaki. They get out these blowtorch and start searing the top of your salmon, right? You're going to get a char crust, a really well-cooked char crust on the outside, but down beneath is still raw, right? It's still red. So the thermal penetration in this particular fire is just not there. It's really high temperature, but for a really short duration. So in this case, you don't get that much charring. And you think about this as an oven with the door fully open, right? So at some point, you're going to lose all your hot gas. It's not going to impact too much on your structure. So really, why am I showing you this here is because ventilation have a huge impact on the chart that we were going to develop for mass timber and for your structural sort of calculation.
Is it always assumed that all your windows are breaking from a ventilation point of view?
I will also get to that in a minute. I would love to have assumed all the windows are breaking, but there will be rules and regulations that will not allow me to do that. And the other thing is, window is probably one of the hardest things to predict. There's not much research about it. And these days, you not just have single glaze. Single glaze will break quite easily. Like for energy efficiency, you have double and triple glaze, and those guys doesn't break. All right. But anyway, we'll come back to that in a little bit. So why am I showing you this? This is the biggest mass timber compartment fire test that somebody has done. And you wanted to have a guess? Perhaps, what is the floor area of this experiment? Anybody? Just a random number.
100 square meters.
Sorry?
100 square meters.
100 square meters. Anyone else? Wow, I mean, you're a structural engineer. Surely you can gauge what's... Sorry? What do you say?
300?
300. It is roughly about 300 meters square. So it's not really a huge compartment, all right? But this is one of the biggest fire tests that we've done that allow us to study the compartment fire dynamic in the mass timber compartment. So there's a few cameras. This camera here is showing you the condition inside the room. These two cameras basically just show you the length of the building. So this is about 30 meters long. And this is the end of the building, which is about 10. It's 10 by 30, that's roughly about 300 meters square. All right, so in terms of fuel load, we have low-level wood crypts inside the compartment. These are often standard fuel load that we use for fire. The fuel loading here is equivalent to what you would have in a residential setting, right? So imagine this is someone's house. So the wall of these compartments is all concrete. The ceiling is CLT, okay? We have timestamp over here that shows you how the fire progressed. So in 3 minutes time, the fire is basically just blazing. So we don't really have a very strong fuel load. Wood crypt is not a strong fuel load. A sulfur is a strong fuel load. Wood crypt is just slow and steady, all right? So we have a slow fire that doesn't seem to do much for the first 3 minutes, all right? And then the ceiling get involved, right? The second and third is showing you how the CLT ceiling start to get involved. Now what happened is you now have a radiant, basically you have a radiant panel that is re-radiating onto all your wood crypts that is on the floor, right? So about 5 minutes time, you can see the fire has propagated to probably about midpoint of the compartment, all right? It's still, it's still pretty slow, but in 40-second time, shoots across 15 meters all the way to the end of the compartment. So these fire dynamics can change quite rapidly. Nobody really understands this all that well. So if you think about this is just 300. Now if you put 300 with 300, you have 600. You have a sizable room now. You put two more, you have an open plan office. Which your open plan office have a full room involvement in like maybe 10 minutes time. This fire, by the way, goes on for half an hour before it's self-extinguished. So, compartment fire dynamics, especially traveling fire, is still a research sort of topic. So if you have fire engineer proposing to you in your design that he or she is using traveling fire, you might want to second ask that a little bit, right? Because a lot of people might assume a localized fire, which is much weaker than what is happening in reality, right? So you don't want to get caught off during your detailed design that your chart depth of 10, 15 mil is actually more like 50 or 60. That's the end of the structural design. Like, oh, your member sizing is wrong, okay? So just be a bit mindful on that.
Does the fire fire engineer have to detail in like fire blankets or fire curtains coming down to stop that traveling fire criteria?
A lot of time, that's a good question. A lot of time, these fire curtains are more for kind of life safety. Okay. But the thing is, fire curtain is also a bit of a trouble. Because if you come down and start blocking it up, yes, you maybe solve the traveling fire problem, but what about means of escape? Because you can't run through the fire curtain, right? It just come down, you need elsewhere to go. And fire curtain sometimes is a bit, tricky to detail as well. And, what sort of fire resistant rating that you're designing it for? Like a lot of them is 30, maybe 60. But the moment you get into 120, they become really hefty. And it's the cost as well. All right, look, I'm going to move on to the lamination. Okay, why we worry about the lamination? Because right from the beginning, I tell you it's a system, and there's different type of adhesive. If the adhesive that is selected for that particular mass timber supplier is non-fire rated adhesive, then once the heat get onto the glue line, it will start delaminating. Now you wonder why do you worry about the lamination? Is it such a big deal? Well, the lamination for us fire engineer, we're more concerned when it is an expensive surface. So we're talking about floors or ceiling, right? So expensive surface where the lamination is a bit of an issue. We don't worry about the lamination of columns or beams because they have small surface area. All right? So this is what the lamination do to the fire curve. All right? So over here, this black line, what you have is the fire picking up, char develop, okay? So char develop, that inhibits further burning, so the fire goes out, right? If you don't have the lamination, that's fine. But if you have the lamination, you start getting this secondary flashover happening. Right? So basically what happens is whenever the heat source go past this glue line, all these chars start falling off. Char falls off, exposes the fresh timber behind that. Fresh timber will start burning again. So the fire just continue to do a bit of dancing and doesn't really go out. And that's a problem, especially if you have firefighter going into the building. They thought problem is sorted, and then before you know, the room behind them just flash over. That's a big concern. It's quite evident on the heat release rate curve, not so much on the time temperature curve, but you can also see its impact. So all these arrows here, what it is pointing to you is when the lamination occurs. So temperature of the compartment just starting to drop, and then the lamination, fire picks up, temperature goes up again. Like the worst is potentially this particular experiment, which has 2 CLT wall exposed. So it looks like it's already going out, and before you know it picks up pretty much all the way back up to your 800, 900 degrees Celsius temperature. So this kind of behavior is really unpredictable. So if you have failure of your glue line, you have the lamination, that sort of issue, then you need to design it properly. It's not like you can't use those products. You can still use it, but you need to find a way to design properly. Perhaps making sure that your char depth doesn't get to that glue line, that sort of thing.
So we don't usually use that. That's perfect for the fire. Not something that we have normal that is perfect. Or there are different options.
Well,
I don't know.
in New Zealand, what we know is all the supplier is using non-fire rated adhesive. The reason for not using fire-rated adhesive is the factory will have to go through an overhaul to include that because it's part of their manufacturing process. And the other thing with fire-rated adhesive as well is it has a really short shelf life, so they don't last that long. But the thing is, people know about our struggle, Southern Hemisphere, and there's certain glue manufacturer that is coming in to try to open up, new business. So maybe that problem eventually might go.
You can generally pay for from say like Exton, you could pay more for a fire adhesive glue, but at the same thing they won't like it. Cure times. Yeah. And then Timberlake, the new Australian supply, that's all non-delaminating. So there is more.
There's more option.
Yeah. Slowly.
Slowly. Yeah. Okay. But still, the thing is, you don't have to go for fire rated adhesive. I mean, certain situation you will see when I talk about the Timber Unlimited guidance, there's certain circumstances where you absolutely must have it. But the thing is that as an engineer, you can also design so that your charring is not so extensive that it reaches your glue line. If that doesn't happen, then no worries. Of course, you might have to live with less exposed timber, but you know, a lot of decision, a lot of, again, conversation to be had. Now, my last worry, structural strength reduction. In fact, maybe you guys can tell me more about this, because you would have probably seen these strength curve before. So the thing here is this structural strength of timber reduces quite significantly about 100 degrees Celsius. Now, as structural engineer, I will provide you with char depth, you know, if I'm doing performance-based design, but you absolutely must remember to add zero strength layer, because I believe that zero strength layer probably comes from your design documentation, okay? So if you look at a piece of timber, let's just say you're infinitely thick, all right? Somewhere in the middle of your timber, you're sitting at ambient, you're 20 degrees Celsius. Right where your thermal front penetrates into the timber, where the timber decomposes, that's probably 200, you know? Go back a little bit to your char layer, that is where it gets hit by 300 degrees Celsius. So these are the temperature range through a piece of timber that is subjected to heat. Now your 100 degrees Celsius probably is somewhere in here, all right? So you will have between your char layer, so this is your char depth, right? This is your char depth, this is all your char. Between here to 100 degrees Celsius is your zero strength layer, right? Why? Because if you look at these two curves, the one up there is the compressive strength ratio of timber. This one down here is the tensile strength. So if you're designing a column at about 100 degrees Celsius, you only have 0.3 ratio, not percent, of the original strength of the timber left. So it becomes quite soft. And at 100 degrees Celsius, people bend timber to create furniture, right? So just keep that in mind when you're designing beams, columns, you know, load-bearing wall, that sort of thing, right?
The only way you can really actually know is by modelling the thermal gradient or something, right? It's not really to know what's happening, say, in the middle of the column. What are you using to calculate? Because that's far.
There's a bit of heat, there's heat transfer. But the thing is, you see, so there's numerical, and then there's also hand calculation where you make crude assumption that potentially you could do, right? Numerical probably will offer you a bit more saving in terms of member sizing, but you will need what we call a structural fire engineer to come in and do the analysis and show you the temperature gradient and that kind of thing. So I'll have a slide later that kind of talks about that and hopefully covers
But
that.
I mean, for fire check, you usually ignore the chart or check and come up with a gradient and do this stuff. I mean, you are saying that stuff.
No, the thing is, what's happening here is for fire design, I will give you a chart depth. Right? So give you a chart depth.
I mean, you are saying that we consider more than
Yeah, well, zero strength layers. You need to add zero strength because there's the chart depth where the timber completely degrades. If I were to calculate something, I can only calculate chart depth. So that's it. But the thing is, I don't account for the layer where it starts losing strength a little bit. Not fully, but losing a little bit. But that little bit of information is what they call zero strength layer. Zero strength layer comes from AS 7020 Part 4. So for various types of element, you know, you have zero strength layer. And then if you look at Eurocode, Eurocode has different definition of zero strength layer. So in the end of the day, a structural engineer, at some point you will also have to make a decision. What zero strength layer should I use? Like people know what's the standard zero strength layer? Anybody? Sorry? 7, right? 7. So 7 is from AS 1720 Part 4, right? But if you look at Eurocode, like depending on your element, it could be 10, it could be 15, something like that. Like It's like, come on, guys, right? Anyway, this is the world we live in, right? All right, so this is what we don't want to see happening, column buckling, okay? Because the cross-section area is too small. Now, this picture over here is actually quite interesting. I don't know if this is a problem, but I thought I'd show it to you and see if my fellow structural colleague can tell me. So what we have here is actually a compartment with a glue lamp column, glue lamp beam, a CLT floor, all right? They do this compartment fire experiment, and at the end, what they found is the column is a bit tapered, right? A little bit short, a little bit skinny, slender at the bottom. And you might wonder, like, well, why does this happen? I thought the compartment is all uniform and stuff, like, you know, your single room involvement, everything is 900 degrees Celsius. Well, not quite, okay? So if you pay attention to some of the compartment fire photos that I've shown you, you will see hot gas coming up top of the opening, right? And fresh air is coming in at the bottom, right at the interface, where you have a lot of potentially unburned fuel going out, fresh air coming in, you get enhanced burning. So it's extremely hot at that particular region, right? And fresh air coming in, if you have a lot of char already developing, that fresh air just helps oxidize the char. When char get oxidized, they turn into ash. They just flake off, right? So this is what the researchers are suspecting have happened to cause this column to be a bit tapered, right? Is this a problem, Ali? Maybe, don't know. It's getting a bit too researchy, but okay. So I just throw that out there. I'm a fire engineer. I just throw problem out there, and I hope everyone solves the problem for me. Right, so let's move on a little bit. Like, it's getting a bit too dark talking about all these challenges, but we do have a bit of light at the end of the tunnel. Guideline that we have on mass timber at the moment, you know, like I say, it's work in progress, right? But we're going to talk about now very quickly about prescriptive, performance-based, and what are the solutions that potentially we might have to try to resolve the lamination, strength reduction, that sort of issue. All right, so in terms of document, these are all available online. If you don't have it, I suggest, you know, maybe you download it, you know, get a copy. These are all on Timber Unlimited website. What we have is a supplement document. This is very short. I suggest you start with this if you wanted to. This is about 15, 20 page long. It describes a lot of the guidelines, the general rules and ideas around how to deal with mass timber and fire safety. This is a much bigger document, 150 page, 200 page of commentary, various chapters talking about, you know, fire dynamics, the design of connection, fire separating, assembly, fire spray, etc., right? So, like I say, our document is just, these documents are just supplementing the fire compliance document. So when a fire engineer uses these documents, he or she will still have to do the usual means of escape, internal, external fire spray, firefighting, as per the compliance document, right? So if the fire engineer is doing alternative solutions, still some of these guidelines are good basis for a fire engineer. Now, what happened with prescriptive design, right? So this is when I just read the table, and I quite clearly do not care about the fire dynamics that is happening inside the compartment. So you will find this in the supplementary document. Basically, you have two main columns, all right? You have sprinkler protected building and unsprinkler protected building, all right? You have two sub-columns that tells you how much exposed wood you can have for different escape height, all right? The higher the escape height, the more risky the building is. All right? And the other columns talk about the minimum fire resistance rating for the building. So really, if I read this table, I can give you, structural engineer, straight away, what's the fire resistance rating for our structure. And I will tell the architect, and he or she can be happy of how much exposed wood he or she could have in that particular design. Now, as your building becomes more risky, naturally, the amount of exposed timber you can have reduces, and naturally, the fire resistance rating goes up. So this is just, you know, reading the table. If the fire engineer happens to do performance-based design and the escape height is not too tall, inside the supplement there's also relaxation for those type of building, even though you're on the performance-based design, but there's still easy way to deal with timber and fire resistant rating. You need to satisfy a few requirements, mainly relating to firefighting, all right? And then you're allowed to have exposed timber and fire resistant rating that a fire engineer calculate by standard methodology, right? There's no need to consider chart that kind of stuff, right? So really what I'm saying here, no consideration about fire dynamics. We don't care, we read the table, I'll give you the fire resistant rating. You will then multiply it by 0.65 standard charring rate, and you figure out your char depth for sizing of your column beams, design of protection to your connection, that kind of stuff. I leave it all to you. But still, you have to add in your zero strength layer if you need to for your design, right? So this is pretty standard stuff. Like we like doing prescriptive design. But not always. Like sometimes you trip into performance-based, and it's quite easy because if you have interconnected floors, like for example this university here, all floors are interconnected. The interconnected floor area is too big, or if this is a hospital, we have managed evacuation. Automatically, I have to go start doing performance-based design. There's no latitude for me to just read the table and be done with it. So when we do performance-based design, the fire that we're talking about is a burnout fire. What is a burnout fire? A burnout fire means that fire ignite, grow, gets to peak, have to decay, timber have to stop charring. That's it. You have to design for the full spectrum. Okay? There's not like, okay, I have sprinklers, so my fire will never proceed beyond that. Or at the end of fully developed, I have firefighter coming in, putting water on the fire, so I don't have to design. There's no latitude for that. You have to design for the full spectrum. So in this particular case, I would calculate the char depth. So this is the difference from the previous methodology. The previous methodology, your fire resistant rating is already there. It's already there for you to use. You multiply by the standard charring rate, you'll be done. But here, I have to do a char depth calculation. The char depth calculation depends on, and this is the stuff that you know for the first few slides, the fire load, the ventilation, the amount of exposed timber. So all these factors governs the char depth. And eventually this char depth, you will use it, you will add zero strength layer, and from that determine the fire resistant rating. So a 60-minute fire resistant rating, standard charring rate, what's the char depth, roughly? Anybody? Any guess? 40 mils, right? 40 mils. If I were to do a calculation based on all this factor, still for a 60-minute fire, I might end up with a char depth of 55. And you as structural engineer will wonder like, what are you doing? Like, isn't it always 40? Not quite. Not quite when you do a calculation. You read a table is 40, you do a calculation, be something else. So you have to wait for me. You have to wait for me to pass that information to you to enable you to size these members properly. And this is hard because there's 3 variables here that is all playing a role towards that fire, right?
So in terms of, for example, CO2 layers thickness, these stuff is still part of the fire. It's an accurate calculation. If you change it, you need to redo the calculation.
Exactly, Ali. That's the painting. And that's only the timber. If the architects start changing the window sizes, anyway, let's not go there. All right, let's talk about solution and less about problems. Okay. Anyway, what I wanted to show you here really quickly is just the impact of timber, the impact of ventilation. One graph summarizes it all. So really, by now you probably will know how to read this thing. So vertical axis is what I call fire severity or fire resistant rating. It has a direct relation with the char depth. So, as char depth goes up, the fire resistant rating goes up, basically, right? Horizontal axis, don't worry about the number. This is all about ventilation. So what I've put here is a nice color graph to show you what I meant. All the way on the right-hand side, a lot of window is breaking. So when a lot of window is breaking, the gas is leaving. If the gas is leaving, there has less impact on your structural element. All the way on this left-hand side, is where ventilation is limited, right? You might have double, triple glaze that never breaks, or I've been imposed a particular requirement that I cannot break more window than a certain amount. This is it, probably, right? So in this particular case, that side, 64% of the window of an apartment is breaking. Here, it's reduced down to a third, 20% of the window is breaking. There's two lines. So the blue line is where we have exposed timber, say exposed ceiling, exposed timber on the wall. So those are the fire resistant rating going up as you do different calculations considering window breakage. So a lot of windows breaking, you have low fire resistant rating, okay? And as you go up, you go from a 60-minute system to a 90-minute system to 120. And before you know, the calculation actually have no conversion because the char depth is just running away. That's my calculation, right? Now the thing is, at that point, I might tell you, look, we can't do that. There's no fire system to cope with that. It's pointless. Let's start encapsulating, right? So if you encapsulate all the timber that was just being exposed, you collapse actually down to this red open circle. So you can see that this is an exponential relationship where a slight change of window size could mean a difference between 90 or 120 or 30 and 60. It's a huge difference for cost of a building, really, right? But if you encapsulate everything, you're still going up, but you can almost see that this is more like a linear relationship than exponential. So really, that's the difference. That's the difference. Why some of these mass timber projects you heard struggle at times is because of this kind of relationship, really. So the important thing here is to know this early, to design around it, to communicate. So if you imagine this is being tabled at detailed design. Like somebody's gonna lose their head with this kind of relationship, isn't it?
I'm just on that. Where does, say, an apartment sit on the curve versus, say,
it will be a different curve.
the AV dash over A, that's area of openings to the floor area, right?
Yeah.
So 0.25 is that, what sort of building or use has 0.25 compared to, say, 0.10?
I have a good bit of research actually on that. I can't quite remember the number, but just from memory, somewhere around here, 0.1, 0.15-ish. That's like your care bedroom. It's only one window, so it's very limited in that kind of situation. Now, if you're a little bit wealthy and you can have a penthouse with nice glazing, right? You're somewhere here, 0.2, right? When you do open plan office, and what you have is a curtain wall because you're so rich now, right? Then you're actually exceeding 0.25. You're right there, but the rules and requirement doesn't allow you to break all of that. So there's a cap to it. We're always capped at 0.25, right? So even though you can have a lot of window, it's been restricted to 0.25. In typical fire design requirement. And the thing is, and I think to some extent, nobody knows why are we sticking to that? Why can't you have more breaking? It's because nobody really knows how these breakage of window can happen. It's almost like random. Do you think that they're all going to fall out? A lot of time the window break and it's just cracked and it's just a bit of a gap. So it's really hard to understand, right? No, it's a very good question. All right, so let's talk about solution. All right, so at some point, you have too much char depth. All right, you already went past your first glue line. Your layer is delaminating. Okay, the fire engineer come and tell you that, hey, look, we need to get this under control. So you need to think about encapsulation solution. One easy solution is plasterboard, right? Board protection, right? Cover up your timber area. There's also another more intuitive or innovative kind of approach into intumescent paint, right? So this two picture here, all the way on the right-hand side, what you're seeing is this part of the wall is exposed timber. This part is painted with intumescent paint, right? So intumescent paint activates 200, 300 degrees Celsius. They basically grow another char layer on top of the timber, right? So when we talk about encapsulation, we actually have a performance that we're striving to. So an encapsulation system must prevent the temperature of the timber surface from reaching 300. All right? So obviously you can see this side of the wall is struggling. I mean, you have char, so it clearly shows that it reached 300. What is that? That is a layer of fire line, 13 mil fire line, under standard fire for 60 minutes. Charring is happening. Now, if you wanted to prevent charring and therefore meet the encapsulation requirement, you need 2 layers, right? 2 layers of 13 mil. This side, no problem, right? There's no charring, right? There's no contribution of your timber to the fire, right? So if you look at the latest, I don't know if people have access to these fire rated systems. Recently, JIP releases in this September 2004, a whole suite of encapsulation system for walls. Now, I wanted to point to you this particular example down here, which is direct fix and batten. So you have a 13 mil fire line being direct fixed onto your timber, and then you have a batten cavity, another layer. This guy is good if you have services running through the cavity, because otherwise you will have to fire stop them for all these other situations. This particular system here just allows your surfaces to run freely, unsealed penetration, right? Similarly for floor, okay, direct fix, suspended ceiling system. Now when we talk about, so that's ceiling. Now when we talk about floor, it's actually the top side of the floor, right? Top side of the floor, there's also an encapsulation solution, and typically that's with a non-combustible lining going over the CLT floor. You have to be at least 15 mil thick. And a lot of time they will, for CLT floor, because they perform quite poorly from an acoustic perspective, there's often this cradle batten system being put over the top. And if the cradle batten has a non-combustible lining, then you automatically meet the encapsulation for your floor surface. So you can save a few surfaces. Like a lot of time when you do timber building, the floor is a guarantee, because nobody wants building that perform very poor acoustically. So the entire floor is going to be covered anyway. So you don't have to specifically try to expose that. You can expose the wall or the ceiling, which is a bit more attractive, right? Now, metal and timber interface. There's no easy way of saying this other than you should avoid or minimize. Because whatever you could see, the fire could also see. So if you can see metal, the fire will see metal as well, and then the metal will heat up, and the timber behind it will char. Again, similar protection you can apply. You can apply board protection, just board up all your steel work, right? Or you can intermesson paint it. But if you intermesson paint it, now you've got to think about what is the limiting temperature of the intermesson paint and for how long, right? Those are key factors that you will have to bear in mind. So I'll just quickly compare and contrast this. So what we have here is an RHS, right? And we have a steel plate going below it. Next to it is a CLT. These are the lamellar dimensions, it's 20 and 40. There's a bit of a gap between the RHS and the edge of the CLT floor. It's not touching, but the floor is sitting on top of the steel plate, right? So you get that configuration. They do this in standard fire test, so all the steel are unprotected. What we have is 71 minutes of standard fire test, and if you just roughly estimate 60 mil of charring, all right, that's about 0.9 millimeter per minute of charring, and you can see what's happening here. This is all char and gone. And what if your floor have some kind of a loading, which you ended up with that particular condition up there, where char progressively getting crushed, and then timber being pushed ever closer towards the hot steel, right? Solution. Well, this particular test here, this result here, what it shows you is when they intermesson painted the steel plate. So the intermesson painted to 600 degree limiting temperature for 60 minutes. So during the fire, this steel plate would have intermessed, so there will be additional layer protecting that. So you will see that this part where it's still exposed timber, the charring rate is still pretty high, 0.9. But over here, because the steel is protected, you have a little bit less charring rate.
It's definitely just from the underside.
Yeah, the fire is from the
How
underside.
about the intermesson? Or is it the whole?
Sorry. The intumescent pane is just to the steel plate. Just to the steel plate.
Around.
Not around the RHS or that above.
What about when they say, well, introducing paint won't work because it's got a timber hard up against it? Introducing paint won't expand.
It needs.
The timber will do the job.
Yeah. Well, the thing is, you see, that's a good question. There's a lot of debate around that, and I think a few paint suppliers have gone off and actually do specific tests to try to understand that. So I know what you mean. What you're saying is, what if you have a few timber blocking here, hard up against the steel, and then that part wouldn't intermesh? Like, what's going on, right?
Yeah, but the timber helps to protect it as well.
Yes, exactly. You're overcladding it. You're overcladding it. Like the timber might fall off, and your paint could still intermesh then, potentially. But these are the sort of grey area that nobody.
What about introducing paint on timber rather than it was only a smoke protection rather than a...
Different type of intumescent paint. There is, like for example, if we just go back quickly, this is an encapsulation paint. This has been put on a CLT. So there are paint system, which is to provide encapsulation, and then there's paint system that is to provide the group number, the surface finish performance.
So the encapsulation one is not clear.
White. Yeah. That's the thing. A lot of clear intumescent coating is to provide surface finish protections to achieve group number, that sort of thing, right? So they are clear, and they are clear for a reason because the architect still wanted to see the timber, correct?
Painted in white paint, otherwise still there anyway.
All right. So let's move on a little bit. So again, metal timber interface, hide them, right? If you have connection, recess them. There's a chapter in the commentary which will be quite useful if you're designing, particularly designing connection, that you should look at. It's chapter 8, right? There's example for knife plate, beam column, joint detail, and then there's also calculation for bracket, beam, and column. But really, what I wanted to summarize here, the whole idea is the total depth that you need to allow. This particular picture here shows that is the char depth that you calculated, and also what they call the sound timber depth that you have to include in there. Right? So there's some example in there that will help you around. Now, we're on to the last part of the discussion already. Sorry, I might have run over time a little bit, but really this is to summarize our discussion so far. Okay, we primarily we talk about the fire challenges, what fire engineer worries about, and hopefully now you as structural engineer hearing that you worry about the same thing as well, and we're all on the same page. There's some guidelines that will help us, right? I've only just talked about generic solution, so now I'm going to use a couple of case study example to kind of show you what kind of level of communication or conversation structural, fire, and architect should have to try to come out with almost like a best case scenario for now. Like everything is constantly evolving, new technology is being developed, but this is where we get to so far. All right, so our journey, PTL journey on this mass timber fire safety aspect probably started with Auckland City mission project, right? This is in 2020, right? So if you look at all the guidance that has been provided, is in 2023 and 2024, right? 23 and 24. So at this particular point in time, nobody know a thing what to do here, all right? So what is this building? This is 10-story mixed use, all right? They have vehicle parking, retail, office, care sleeping, and also normal sleeping accommodation. So there's a few at-risk occupant for this particular building. Level 1, level 2 is concrete structure, and the rest up above is CLT wall and floor with steel work. All right. So PTL, we're involved actually very, very late for this particular project. We're not even doing peer review. We're assisting Auckland Council doing consent review, and there's already a PS1, a PS2 at the standby for this particular project. So it's really, really tough. But the outcome of this is we managed to convince the designer that, look, you need to think about encapsulation some of these walls because they are all they're covered but they are not encapsulated, because now we talk about specific performance of encapsulation. You need specific system to limit the temperature of the timber to no more than 300. They're putting normal JIT plasterboards, standard plasterboards. It's going to fall off in 15 minutes, basically, right? So we managed to convince the designer, look, you need to add a few fire line here, a few fire line there, get to this particular performance and get it done. So at the end of this project, we realized that the industry, New Zealand industry at least, need a lot of help very quickly, because this is just one of the first. There are many more to come, right? So the next year, we actually got a little nice project ourselves, all right? So we're the designer for this project. There's a townhouse at the back. That's just plasterboard construction, no mass timber in there. But the mass timber come with these apartment up front, right? It's a 5-story. The first level is concrete with a concrete podium, and then you have mass timber structure up above. All right, CLT wall, floor system, steel work. Very similar to what we have at Auckland City Mission, because again they are small residential sort of apartment. We probably don't need to do this. I mean, by today's guidance, this would be a 15 minutes, half an hour job of just reading a table and tell you that it's sprinkler protected, so fire resistant rating is 60, please, and tell the architect, you can expose 200% of the floor area as exposed timber. So if the floor area is 200, then you can expose 400 of timber surface. But we've gone the long way, because once again, at this point in time, there's no guidance. You go talk to Auckland Council, they say, oh, you're using this new technology. Why don't you do a full alternative solution? And before you know, I'm crunching chart depth and try to convince my structural engineer that 60 minutes is not 40 mil chart depth, but it's something like maybe 50.
Is it also with the alternatives that can be reduced? The charring rates?
Normally, the table is nicer.
Okay.
Table, when you don't have to think about fire dynamic, it's a simpler way of living. So just cancel that from the record. All right. Anyway, look. Let's have a look at the detail. Right. So what we have for this project is encapsulation to the wall and floor system. So floor again, floor is the acoustic cradle and batten. 20 mil non-combustible lining going across. So that's the dash line that you're seeing. We have a 30 mil fire line being batten fixed onto the CLT wall. All right. We make assumption that the ceiling will fail, although we actually encapsulate the ceiling. So all these red line, other than the top side of the floor, you're seeing 13 mil fire line, right? But back then, because we don't have too much of a guidance, the reason we worry about the ceiling is because we have a lot of penetration. So we think that our ceiling could potentially, fall prematurely, because we're not planning to stop all these, light fittings, etc. and whatnot. So, eventually the fire will creep into the cavity, burn all the battens or rondo fixing off, and then before you know, the whole encapsulation is on the floor, right? So this is our assumption, which is why we say that, look, we assume the ceiling fell. These days, we might not be allowed to do this anymore, all right? Because, JIP have the system of direct fixing and a batten. And that's where you're allowed to run unsealed penetration. But back then, again, we don't know much, right? So we make the assumption that, look, any penetration that is going through our fire line of the wall will be very small. You're looking at stuff like that. So the timber behind, if anything goes wrong, will be quite localized, right? Tough. Right, 2022 is when things get a little bit more serious for us. We are the peer reviewer for this Avida retirement village. What they're doing here is 3-4 story retirement complex. They have basement and level 1 made out of concrete. All the structure above, again, CLT wall floor system with steel work. Okay, so we're the peer reviewer of this, and it is very interesting because we now see a lot of complex steel and timber interface for this particular project. So what I wanted to point out to you over here is if you focus on this picture on the top right, what it is showing you is a CLT floor with a steel column going straight through it, an I column going straight through it, and there's steel beam coming into the steel column, being bolted onto the steel column. That's that particular detail. So again, back to the concept of system. This is a system. You can't look at things in isolation. You got to look at this particular junction here and say, what do we do about it, right? So for this particular project, a lot of these apartments has encapsulation to the wall and floor. The ceiling is not encapsulated. So you just remember, in event of a fire, the ceiling will fall off because there's no encapsulation there. So this presents a little bit of problem to this guy. All right. So column, how do we protect that column going up? Is a bit of a mix. All right. Where the column is exposed to the occupied spaces of the building, we have board protection, right? So the steel is not painted in there. It's board protection coming down, and then above the floor is also board protection. But in the middle, where all the steel beam is intersecting with the column, and you have bolts connection and all that, that part is intumescent painted. All right, so you have board, intumescent paint. The CLT floor sits on top of these intumescent painted steel beam. Now the only issue now here is for the steel column to go through, you got to create a notch in your floor. So you got to cut a hole in your CLT floor, and it's an I column, so there's a lot of gap. So that gaps will still have to be filled up because why? Because in the event of a fire, the ceilings fall off, right? The beams have all intermessed, right? The column, you still have bolt protection, and some part of it where the beams intersect will also intermesh, but then you have all this gaping hole, right? So what we ended up fixing is a bed, a fire-rated bed that is being cut to cover up, the remaining space between the columns and the floor, right? You get that picture, right? So, and then the other thing what we do is we make sure that there's a bit of overlap between all these fireproofing systems, right? So there's a bit of intumescent paint going above the bed, right? There's a bit of intumescent paint going below into the boxing of the column beneath the floor, right? So it's tricky, and, we don't admit that this is greatest, all right? But it is what we could do at best at the time, right? Probably 20 years from now, somebody will just say, why don't you just use that system, all right? Anyway.
The size of the mat is just about the whole of the
So the size
of the mat.
the bed.
Bats are.
Yeah.
It's much bigger than one size.
No. So it's been fusion fitted. Yeah, fusion fitted into there. So I will talk about another example, which is also bad, but the bed couldn't go in. Talk about that.
So does it mean change the open section to a closed section, such as SHS or IHS will help for the steel column?
Yeah, we'll make it better. And you concrete fill inside for me, please.
Is that course?
All right. So the thing is, you got it right. So you can change things, right? You can change things, and we need to discuss again. We need to look at that detail again. We need to communicate. We need to figure out why and how we can do certain things. Right?
How do you get the add-ons? The two pieces, or do you have to spread it down the top of the building?
I don't quite know the detail, but I imagine they will cut it. They will have to cut it to kind of fit the profile. Yeah. And then you mastic seal it. What you can't see is there's a lot of mastic going around it just to hold it in place. All right.
Sometimes even you draw this in the detail, but you also need to have on-site inspection. It's very hard to achieve as well sometimes.
Oh, you got to get the sequence right, please. Because before you know, everything closed up and you ask the contractor, did you remember the guy coming around and put the bed in? Oh, I think I have photo. I think I have photo. All right, and the other thing is this design is this building design is complex because a lot of time you have the sort of apartment at 30 minutes, and then you have all this communal area, right? The communal area then cope a 60-minute fire resistant rating, right? So this is what it is showing you here. So some part of this floor is actually 60-minute we run encapsulation, and again, we come across quite a bit of steel detail. There's a PFC supporting the floor, and then there's an I-beam supporting the roof because, you know, the different levels and stuff. So again, there's a lot of communication around here. Like, you know, what do we do? Like, is the intermesson painted steel enough to act as encapsulation for the edge of the CLT floor, you know, or maybe not, or maybe we should just run the plasterboard around it and forget about this problem. So, you know, a lot of communication, really. So architect, structural, fire, you know, you have to talk to one another. All right, so this is a project that we're fortunate enough to be involved in. So we're the fire engineer for the K Road project. You might have heard this particular project in the news for a bit. So it is a 10-story office building with 2 levels of concrete basement. The floor above, you know, CLT floor, glue lamp column, beams, braces with some steel work. This is absolutely alternative solution. There's no way you can just go read a table and call it a day sort of thing, right? So it's alternative solution, and it presents a very big challenge because if you look at all the case study before, it's all small room. It's all small apartment we talk about, you know, it's guaranteed full room involvement because it's so small. Like a lot of our design calculation is empirical and analytical in nature, and they've been developed for small room. Now you apply that here, it's a bit of a stretch, right? And you've seen already that 300 meter square compartment, how quickly the fire get to the end in the last 40 seconds, like what would happen here? So I don't have all the answers. I'm the designer for this, unfortunately. So sometimes, you know, you can't solve the problem directly. You will have to kind of solve it laterally. There's other consideration, other system, for example, sprinkler system, you know, upgrading it beyond what is required typically by sprinkler standard to try to cope with this kind of situation. You know, give your design a bit more robustness, you know, a bit more factor of safety. That's all you can do, you know. All right, so at this note, I wanted to just point this to out, okay? This is for tall building, so or sort of tall building. So when your escape height exceeds 18 meter for sprinkler building, or when your escape height exceeds 10 meter for unsprinkler building, you need to do these two. You need to make sure you have fire-rated adhesive for your CLT floor, and you need to make sure that any freestanding column or load-bearing CLT wall of your building is fully encapsulated unless structural design is able to consider the maximum internal temperature of that particular column caused by fire. So I'm trying to answer the question raised by this gentleman, you know, probably half an hour ago. Right, why is that? Why are those two requirements there? Firefighter, right? Firefighting capability. This appliances here, this appliance is the one with the highest reach, and is only reaching 22 to 25 meter tall, right? Spraying water upwards. I mean, you're a structural engineer, you can tell me that gravity, all about gravity, you know, is hard work, right? So which is why 18 meter and 10 meter comes in, so that firefighter, you know, can deal with it nicely. Because any taller, they can't use these appliances. They have to go into your building. Now, if your load-bearing wall and columns are just buckling, or your floor is delaminating, you can see that they might not be too pleased, right? So that's the reason for those requirements. Now, what do we do for this K Road project? So we have an encapsulation to the ceiling and the floor. So again, I'm trying to answer the gentleman's question about how much ventilation I was allowed for this particular calculation. I can tell you that I break 60% of the window. All right? Sounds like a lot of hot gas is going out, but that's still not enough. I have about 55 mil of char depth. Now, if you know your lamella well, the thickness well, I'm now in the second layer, which means I moved past the first glue line already. Right? And if I don't have fire-rated adhesive, then that's going to be a problem for me, because my calculation doesn't assume delamination. A lot of these calculations that I'm doing, calculating 55 mil of char depth, is assuming no delamination. Now, if it's delaminating, like my engineering justification doesn't hold, right? So which is why, we have fire rated adhesive. On top of that, because of our height requirement, we are 45 meters up in the sky. All right? And firefighter cannot spray water that high, and they will have to go into the building. They don't want the column to be buckling. All right? So, so what do we do with the column beam braces? They're not encapsulated. So in this particular case, open plan naturally means no wall. We don't have to deal with CLT wall yet. Right? Now what I'm showing you here, this GIF is just running by itself. We look at the decay phase analysis because the client doesn't want the column to be encapsulated. So we have to make sure that the column is sized properly to account for the internal temperature induced by the fire. Because the thing is, once your fire go out, it's not like you turn off a switch. The thermal wave will continue to propagate into your column because your column is still hot. It's not because the fire stopped, the thermal wave is just going to stop. So what I'm trying to show you here is there's a fire being imposed on this glue lamp column on all four sides. And it follows a time temperature curve similar to this. So it's taking us a while, so I'll just restart it. No. All right, it's almost done. We'll just wait for it to stream. So what you have is the temperature. So now your fire started. It's imposing a temperature on all four surfaces of your column. So you can see the red, that's above 300, so it's charring in, right? And just focus on the blue patch in the middle. That's your 20 degrees Celsius, right? So now the fire has decayed, right? So you can see the edges has cooled off, but just focus on the middle, 20 degrees Celsius. It continues to propagate, it continues to eat into your column, right? So if you think about where the 100 degree Celsius is sitting, your column is continuing the shrinking. So now, if you've done this analysis and you can figure out what's the maximum temperature reach along the fire until the fire has gone out for maybe another 2-3 hours, everything returned to ambient, you arrive at this particular bar chart over here. So what I'm showing you is different mesh size for the numerical analysis. They're all for the same column. The column is 600 by 600, so I'm just showing you half of the column. The 0, the outer is the outer surface. 300 is smack in the middle of the column. So you will see during that particular fire that was imposed, we have about 60 mil of charring. All right, all this color along here. For the next probably 90 mil is when you get to 20 to 30 degrees Celsius. That's your 20, 30 degrees Celsius range. Right? So if you say, look, I'm going to discount everything 100 degree and beyond, so I'll discount 100, 200, and 300, not going to use that for my loading calculation, then you're probably looking at this particular line here. So this is where your 100 degrees sits. So you have about 210. 210 multiplied by 2, you have 420 of section left. So is that enough for the loading during fire? All right? So if it is, then you've sized your column correctly. But if it's not, then maybe make it a bit fatter for me, please. Thank you. All right? So last project here, this is happening in Hastings. So not all offices building has to be alternative solution and very complex. Some offices, you'll be able to fit it nicely under acceptable solution, in which case you read the table, you do a prescriptive design. I told the architect you can have W200, so 200% of the floor area can be exposed timber. So if you're 1,000 meters square, you can have 2,000 meters square of exposed timber. Use it wherever you like, right? 16-minute FRR, told my structural engineer, happy days, go off, do the charring calculation, design the connection, column, whatever, all right? So that's it, but still, we have to encapsulate something. So in this particular project, we're encapsulating the floor naturally, and one requirement requires us to encapsulate the back wall of a services riser. Right? Services riser can be quite messy. It's a continuous continuous shaft. So if you have an entire mass timber surface exposed and you're running services, which might be electrical cable, etc., then that's a bit of a risk in there. So batten fix 2-layer of fire line onto that CLT wall. There's the usual coordination of fire stuff, doing a bulkhead. So by the way, this is a section of the riser, right? You're looking at the section of the riser, services coming through here and going up. We have to build a bit of a fire rated wall and then jib shaft wall system all around, going up. The column beams and ceiling in this particular project, non-encapsulated, is all fit within that W200 requirement, so that's pretty easy. But we do have steel EBF, so lateral restraining system going up the building. So again, what you see here is a steel column going straight through the CLT floor, a beam, and then angle braces, right? So we interrogate two options for the design team, for the QS to quote out and decide, which one is better. So there's this boarded system where you just board up all your steel. And as a result of boarding up the steel, you also solve the problem of your penetration. So these two are notched into the CLT floor. And then these two on either side are the continuous steel column. So you encapsulate the bottom, encapsulate out at the top, doesn't see the hole, no problem, right? Now, if you go into mess and paint, right, you can into mess and paint the EBF, no problem. But then you're left with all these holes because, again, you have that I section. You have that I section going through, and now you have a brace coming in. So this particular hole over here is not that easy because previously with the Arvida project, the hole was just nice and square, right? So you can fit the bat in there, you put some mesh stake, will stay in place. But in this case, around this angle, you have to shave off a bit of a bat and stick it up, and it just doesn't stick. Like, you call Ryan Fire is one of the passive suppliers. I call them, they shake their heads. They know our product doesn't work this way. So this might sound like a wonderful idea, but if you interrogate further, a few phone calls, a few conversations, you might kind of go like, well, let's not go down this path. Right, so communication, always communication. Anyway, that's the end of my presentation. Sorry I ran over time. I would like to acknowledge, quite a few organizations here. So thanks for having me, ASG. Thank you.
What is far right adhesive much more expensive?
I think it's a supply and demand thing, probably.
Can't get it.
Yeah, it's just, we're a little bit far away. So,
What is it called? What kind of glue is it? What's it called?
it's the one supplier that we know is an organization called Henkel. Henkel, they make different type of adhesive. So there's the non-fire rated one. They also make the fire rated one. There's HBX, the next. So I think they're coming to Australia. That's the news we heard. They're setting up plant. So supplying into New Zealand.
Don't you have to get your screws from Germany anyway, so what difference?
Shelf life, is it? The shelf life of the fire rated adhesive. They don't last that long. The screw will last quite a while. I hope screw lasts a bit longer.
They also have problems with the fire testing, right? Like they just spent like 10 years of fire testing, like normal PURs, and now you go change your glue, and all your fire tests are essentially.
We had this.
It's fire rated. It's fire rated glue, but it doesn't.
Yeah, you can like to.
Yeah, you will be better. Like that's the debate that we have in the office. We almost say like if you swap over, you swap over, because you're using something that is better. So your performance should be better.
What's your take on like gaps and what like 2 mil or 5 mil? Like,
You worry about that? Oh, you worry about that? I would.
Like, I think Eurocode sort of 2 mil, and then other people sometimes they use 5, some people use
I think
less.
I mean, for us, it's really anything more than 2, you should survey.
Do something with that.
Yeah, I mean, that's the thing with timber, like, once you build it, there's moisture, there's this and that, you can't really, it's a living thing. So the thing is, when it gets dry, these cracks start happening. So this is what I kind of go like, don't design your building to the limit, especially with timber, make sure you have enough other things going on. And I'm not saying that for all your risk, because I mean, if you're just doing 2-3 story walk up, I mean, come on, you don't know you need to get out of your home when it's on fire and use. But if you're doing, 20-30 story high rise mass timber with interconnected floor and stuff, then you gotta, you can't solve mass timber problem by just applying, passive or fire resistant rating to it. I mean, there's other stuff like fire engineer. I mean, we know. The first thing is sprinkler is our best friend. Like, I mean, sprinkler also have latitude to increase in its performance. Like you have a residential, you will typically just do DLH, extra light hazard. That's the lowest, sprinkler grade. But if you go up 20-30 story up in the air, well, maybe think about, increasing it a little bit. It doesn't cost that much. Like the cost of sprinkler is, do I put it in or do I not put it in? After that, is selecting the right size of pipe and the right size of head. Like, that's it. And, yeah. So, any other questions?
So with the dowels and how you've got them embedded into the triangle, is there any way to avoid that? Like, because, like your dowel and it's embedded in your triangle, you've got a very small plate that you can rely on. Like, are there any products that you can kind of put in to block that?
If you can see the steel, I will see the steel too.
Yeah.
It's about hydrogen, or you can think about intermittent paint. But intermittent paint is a bit challenging because the whole idea of intermittent paint is you need to figure out what's your section factor, the heated perimeter versus area, and when you come to connection, what is it? Right, so it becomes challenging. So really the thing here is you try to hide your connection. It's pretty much or you otherwise you fall in.
Yeah. So like if you have an embedded dowel and like let's say you're not wanting to embed it all the way into the triangle, is there a product to provide to kind of reduce that depth of embedment or not really?
So what we do is just pack it with sacrificial, but then we make it very hard.
That would be like a chart, it has to be a chart.
Yeah, charring that, and then there's that sound timber back or 7 mil. And different configuration, you will have different equations. Like I said, I'm not structural engineer, so you need to look at your guidance document. And I would say chapter 8 of our commentary, again, you can find that online. Have a look at it. There's a couple of examples, probably not the scenario you're describing, they're talking about knife plate and brackets. But yeah,
So here there's only a 3-story hotel and you want to clad it all in chipboard, and you get you convinced the structural engineers that the chipboard bracing works on the ground floor. And then you got your bracing and your fire rating at the same time instead of having plywood and then chipboard on top. And you get your cell rating as well. Well, I mean, the often say that it doesn't work, but obviously it does. But
how many walls you want?
what do you mean, how many walls?
Part of the byline, jet line.
If you're doing a hotel, all the rooms are, 4 metres by 3 metres or something, so it's all nice regular group and everything all works. But we often say that the chipboard bracing doesn't work on third floor. Well, people in high beds anyway, because the law didn't allow for anything over 3604 or something. But they're busy redoing 3604, so sort of like they say, oh, the law says this, so you can't do it. Whereas someone should be saying, well, you wouldn't want to do it, how do we design it? Rather than saying you just can't do it.
So there's definitely a lot of that, and as you can tell, I'm fine engineering. So This white is dark art, so.
Thanks so much, Ines.